In order to fulfill the requirements of our fluid dynamics and kinematic classes, we, Team Mirage, designed and built a liquid mirror telescope.
The concept of a liquid mirror telescope was first postulated by Isaac Newton. He discovered that if you rotate a liquid at a constant velocity, the surface forms a paraboloid, the perfect shape for the primary mirror in a telescope.
The challenge is, in order to form a mirror, the fluid must be completely reflective, like a metal. Unfortunately, most metals are not liquid at outdoor temperatures. Mercury has all the ideal characteristics, but is highly toxic. Instead, we have chosen gallium, which melts at 86 degrees Fahrenheit.
Our telescope design consists of three primary parts: a parabolic basin, a planetary gear set, and an enormous tripod that holds the camera at the lens's focal.
While the shape of the container doesn't actually impact the shape of the parabola, making the dish itself into a parabola reduces the amount of liquid required. Scholarly research has shown that the density does not play a role in the formation of the parabola, which means that viscosity doesn't play a role either. To dimension this disk to the focal length and the amount of gallium we had, we utilized the Buckingham pi theorem and dimensional analysis to predict the behavior of our lens using water as an experimental substitute. The parabolic shape comes from a combination of the no-slip condition at the liquid container interface and the centrifugal effect. We compared the data with the accepted equation h equals omega squared r squared over 2g. Our data was within the error of our measurement system. This allows us to directly transfer the experimental data obtained with water to gallium.
One of the problems of using gallium is that it melts at 86 degrees Fahrenheit. In order to use our device in the cold night air, we needed to heat the parabola to keep the gallium in a liquid state. We had initially considered electric heating elements, but it was far more efficient to use an exothermic chemical reaction underneath the parabola to heat it.
Our planetary gear mechanism was 3D printed from ABS plastic. The gear train provides for a gear ratio of 13 to 121 in a compact form that adds stability to the device. We used an online software called woodgears.ca to create an approximate and volute tooth profile. We then used this profile to make custom gears in SolidWorks for 3D printing. The sun gear itself is driven by a stepper motor, which is controlled by an Arduino microcontroller.
Based off of experimentation and the limits of our gallium, we determined the radius of our parabola to be 2.9 inches, and we calculated the angular velocity to be 10 rotations per minute to give us a parabolic focal length of 14 3/4 feet. This placed the camera as far as realistically possible to avoid shadows on the mirror. The tripod is 16.5 feet high and constructed from solid wood and 3/4 inch bolts. Nylon rope and pulleys were also used to precisely control the camera's Z-axis position.
But that's not what happened. When we set everything up, we ran into several unforeseen issues.
Thin, high-altitude clouds obscured the stars, making it difficult to obtain a clear image. Even parts of the sky that looked clear to the naked eye had clouds in them, as evidenced by the images we obtained using the camera.
The heating element worked fantastically well. However, the heat was directed downwards and melted the glue used to attach the arm to the planetary gears. Our parabola simply slid off the rest of the device. Meanwhile, the parabola was only mildly warmed.
Gallium has an incredibly high surface tension with ABS plastic. It just sat in the center of the dish and refused to spread out, making it impossible to obtain a parabolic shape.
The exposed surface of the gallium began to crystallize immediately. This gave our lens a rough, non-reflective surface, utterly useless as a mirror.